In this section, we will take our recently transformed Navier-Stokes momentum equation for flow on a rotating planet and perform some scaling to find the leading order balances. We begin with our Navier-Stokes momentum equation and make the assumption that the flow is inviscid, allowing us to drop the viscosity term here to give us the rotating Euler equation. Remember that we have already seen that the Coriolis term here, 2 omega cross u, approximates to having the x and y components of negative fv and fu, respectively, where f is 2 omega sine of the local latitude theta. We will consider the vertical component of this rotating Euler equation. We write it out in full, giving the vertical acceleration and advection terms here. For the purposes of this scaling exercise, we will use the complete omega cross u, giving us a term with the x component of the rotation vector omega and a term with the y component of the rotation vector omega, plus gravity and the vertical pressure gradient on the right-hand side. Recall that the x component of omega is 0, so we can lose this term. Now we would like an idea of the magnitudes of these remaining terms, and we do so with the usual scaling procedures. For geophysical flows in the oceans or atmospheres, the vertical scale h is much smaller than the horizontal scale L. If we take a horizontal velocity scale u, the time scale t can be L on u, and from continuity we can get the vertical velocity scale w as UH on L. Substituting these scalings into the vertical Euler equation returns a quad of u squared h on L squared terms and an omega u term on the left and a gravity and pressure term on the right. We can non-dimensionalize by dividing through by u squared on L, giving a group of h on L sized terms and omega L on u on the left, and then non-dimensional gravity and pressure terms on the right. Let's consider some typical Earth values for these terms. Omega, Earth's rotation, is about 10 to the minus 4 per second depending on latitude. Gravity is 10 meters per second squared, and ocean basins and atmospheric systems are anywhere between hundreds of kilometers right up to the circumference of Earth. For the ocean, the vertical scale is kilometers, with typical velocities of under a meter per second, while the atmosphere is tens of kilometers deep, with velocities potentially up to tens of meters per second. We can plug these magnitudes in to find a fair separation of scales between the left and right-hand sides. H on L, we already know, is less than 1. Omega L on U is up to 1,000 at most, while GL on U squared is over tens of thousands to even millions. So the leading order dynamical balance for the vertical component of the rotating Euler equation is between the gravity and pressure terms, meaning we can ignore the left-hand side here. This balance, of course, is something that you are already familiar with, the hydrostatic balance, which we have just seen remains relevant for flows on this rotating planet.